Video, we are going to look into memory coalescing and band conflicts and going to discuss some benchmark comparing the performance without memory coalescing and band conflicts and with memory coalescing and band conflicts. Before moving to that, let's briefly get the overview of the memory hierarchy in GPU. So there are typically two main memories in GPU. One is called global memory and one is called shared memory. Other memories like constant memory, texture memory are also there, but are very limited. So we are not considering them for further discussion. Obviously, threads are also having some registers. We are not considering them also. So this is the memory hierarchy where each of the thread are going to share this global memory. All the threads within a GPU are going to share this global memory, and then threads within a block will have their own independent shared memory, and all the threads within a block are going to share that. And then each of the thread will have its own independent registers. Now let's move to memory coalescing, our main topic. So if the warp threads accessing elements from same block of 32 words, their memory requests are clubbed into one. This holds only when the data is accessed from the global memory. Let's look into some example. So let's say these are 32 threads and they belong to the same warp. And these are the 32 consecutive locations somewhere in the global memory. Now, since the threads within a warp are accessing the elements from this 32 block, 32 chunk from the shared memory, all the requests will be clubbed into one. So we may think it's making 32 requests to get the data, but it's not. It's just making only one request to load the data from the global memory. Similarly, in this particular case, we had the ordered request. The request look very ordered, but here the request look very random. It doesn't really matter if we are making the request in this particular way or even any other random, as long as the threads are from same verb and we are accessing the data from the a chunk of 32 words, consecutive 32 words, from the global memory, the request would be coalesced. So in this particular case, even if we are not making all the requests, we are making few number of requests, these requests will still be clubbed into a single request instead of these arrow number of requests. Now let's move to another example in which we have these 30 again 30 a warp of 32 threads, and then we have these two chunks of 32 words. Now a single warp is accessing the elements from these two chunks. So here the memory request would be clubbed for this particular chunk and would be clubbed for this particular chunk independently. So we would end up making two requests instead of one, which we were making in earlier cases. Let's move to bank conflicts. This holds only when the data is accessed from the shared memory. The shared memory is typically organized into 32 banks, and consecutive words are stored in adjacent banks. Access to the same bank are sequential. Let's move to the example. So let's say these are 32 threads. These are some threads. We are showing only 15 threads for demonstration purposes, and then we have these 15 banks, let's say. Now, since all the threads are accessing the elements from a different bank, the request to the elements from the memory request won't be sequential. They can be completely parallel because accesses from the different bank can be parallel. In this particular case also, although the requests are not as ordered as we had in this case, but still we are accessing the elements from completely different banks, so the request would be parallel. But in this particular case, each of the bank, so we are accessing two elements from each of the bank, which means that accessing the elements from bank 0, bank 2, bank 4, and similarly for other banks would be sequential. So across bank 0 and bank 2, they would be parallel, but when we are accessing from bank 0, those two requests has to be sequential. In this particular case, there is even more bank conflicts because there are so many elements in the bank and we are accessing them from the same bank, so the request has to be sequential. There is an exception to what we have learned till now. If we have a verb which is accessing the same word within a block, then those requests are not sequential. So in this particular case, let's say these are the 32 threads from the same verb, and then these are the 32 banks. Now, if we are accessing the same element from a bank, so from this 12th bank, we are accessing only one element, or many threads are accessing only one element, and then those requests would be parallel only. They won't be a single request. They won't be a sequential request. Performance. When we are accessing elements from the global memory, memory coalescing is the deciding factor for performance. But when we are accessing the elements from the shared memory, bank conflicts decide the performance. But please note that if there is a huge synchronization involved across threads, then memory coalescing and band conflicts don't matter much, as time for synchronization would be much more than time for accessing the elements from the global memory or the shared memory. So this is the benchmark I copied from the NVIDIA blog post. In this blog post, author wanted to implement the transpose of the matrix, this operation, in a most efficient way. So they did the benchmark on these two GPUs. These are two different GPUs, and then to do the fair comparison and to understand how we can improve the performance, first author copied the matrix into another matrix instead of doing the transpose, and he got this much bandwidth on this GPU. And then he made use of the shared memory and got this much bandwidth. In this GPU it really increased, in this GPU it decreased little bit. But then he did the main operation, which is transfer. He implemented the transform in a very simple way. He didn't really care about the memory coalescing at the band conflicts. He just implemented it. And we know that if we implement transpose in a naive way, then the request, the access request uh, won't be coalesced, because transpose needs to access the elements across, like after a few number of columns, right? So he got very less bandwidth, which is 18.8. Now his target is to reach the bandwidth, which is very close to the copy bandwidth, basically. So what he did, he tried to implement the transpose in the fully coalesced way, and he got this much bandwidth, 51 and 97 for this GPU. You can clearly see that just by doing memory coalescing, he was able to double, a little bit less than double, and for this particular GPU. And then he made use of shared memory and tried to reduce the band conflicts, and he got a very good bandwidth, which you can see that is very comparable to shared copy shared memory bandwidth, which means that memory coalescing and band conflicts can really help us in increasing the performance. Thanks a lot.